Everybody, welcome to the video here for lesson number 4. In today's lesson, we're going to be talking about independent events. To be able to determine whether or not events are independent or dependent upon each other, we need to be able to determine a couple basic probabilities. We need to be able to find the probability of an event happening or the probability of an event happening given a second event. So the opening exercise here is just me seeing, do you know how to do those two things? Can you find the probability of an event happening? Can you find the probability of two events happening simultaneously using the word and? And can you find the probability of two events where one is given of the other? So pause the video, take a moment here, use my two-way table, males versus females, and whether or not you like to pick a Republican, Democrat, or other type candidate, and see if you can determine these three probabilities. Keep in mind, even though it doesn't say it, when you're finding probabilities, always round your answers to 3 decimal places. It's kind of a rule of probability. So go ahead, pause the video, and see how you make out here. All right, so welcome back to the video. Hopefully you paused and tried your luck here on this question. So for the first one, I asked you, what is the probability of being a Republican voter? So to be a Republican voter, there are 461 Republican voters out of a total of 1,000 voters. If I round that to 3 decimal places, I get 0.461. I like to put the 0 in front. You don't have to, it's not a big deal. For the second probability of being a Republican and being a male, so this word and is telling us that both of those things have to be true. It's also telling us that we're comparing this to the total people in this survey. So the number that represents Republican and male is 244. So there are 244 people that are both Republican and male out of the 1,000 people that were polled in this survey. So that would become the decimal point 244. And the last one says the probability of voting Republican given that you are male. Now, this probability and the second probability sound similar, but they are actually very different. This is something that we know. We're not putting that into chance, where this middle probability, the probability of being Republican and male, it's taking into consideration that you could be male or female. So it's using all of the different people that were in this poll. Here, we're only looking at the males. So since we're only looking at the males, I only want to look at a certain portion of these people. So we're only looking at this column here, or this row here, okay, that I'm highlighting here in purple. So because we're only looking at that particular section of this, we're looking at the Republicans here, 244 still that are male, and out of the 470 males that were in the survey. So we're only looking at that one row. We don't care about anything else in this table. So if we go through and find that probability, we get 0.519. Now, looking at these 3 numbers and the 3 things that we determine using those numbers, we should be able to determine whether or not there's some type of an association between your gender and your preferred candidate. So if I look here, being a person out of this whole group of people, males and females, and wanting to vote Republican, there's about a 46% chance that you would vote Republican. If you were to look at this one that was given, this is saying that we want to see what is the probability of voting Republican given the fact that you are a male. So that means we're only looking at males there. So knowing that the candidate is male, the chance of voting Republican is higher than when it was not known whether they were male or female. So these 2 probabilities, since they are different, we can say that they affect each other. Being male affects whether or not you vote Republican. So what we can say is because the probability of voting Republican and the probability of voting Republican given the fact that you are male are different, there is an effect on your vote and or given your gender. Basically, what we're saying here is being a male affects whether or not you would vote Republican or not. Now, is this true in all of America? I have no idea. It might just be true for this one election. It might just also be true for this one sample of 1,000 voters that we found. But with this one sample of 1,000 voters, what we can extrapolate is because this was significant, this did change by a lot of a percentage, right? 46% to almost 52%. That's a big jump, right? We can probably extrapolate that to the entire population in this 2016 election. So this opening exercise gave us the basic idea of what we're trying to get to today. So what are we trying to get to today? We're trying to determine whether or not two events are considered independent. Independent events are two events that we know happen at the same time, but they do not affect each other, right? So independent events have no effect on each other. Now, some events are easy to identify that are independent. For example, the probability of me having pizza today and the probability of whether or not it rained today are not going to be dependent upon each other, right? The fact that I ate pizza for lunch did not change the probability of whether or not it's going to rain during the day, right? And vice versa, right? Now, other probabilities are going to be harder to see. You're not going to be able to see right away from the context of the problem that they're independent, like this opening exercise question, right? I just have a bunch of data. I don't know if being a male or a female is going to affect my voting outcome. So because we were able to show that, there was a distinct change between the vote when we introduced the fact that the voters were male. We can say that these are dependent events. Being male and being a Republican person are going to be dependent events because the probability of voting Republican was affected by being male. Now, there are probably 4 or 5, if I'm remembering correctly, ways of proving independent events. I am not going to teach you every single possible way of proving events are independent. That's an AP stats topic. For this class, we just have to be able to identify some probabilities from a two-way table and be able to say these events are independent or these events are not independent. And I think the easiest way to do that is to show what I have on the top of the next page. So to be able to show that two events are independent, I'm going to find two probabilities. I'm going to find the probability of an event happening, probability of A, and I'm going to find the probability of that same event happening given a secondary event. So this would be like the probability of me eating pizza and the probability of me eating pizza given it rained today. So by introducing B, what we're testing here, right? This test is testing, does B change the probability of A? If by introducing this new event given, if it doesn't change anything, these events are independent. That means there was no effect whatsoever. If these numbers come out to be the same, that means that they are independent events. If these numbers come out to be totally different or slightly different, that means there was some effect on one probability on the other. Therefore, they are what we call dependent events. So let's take a look at an example here. So we have another two-way table, males versus females and the type of subject that you prefer, math, English, social studies, or science. And there are two questions on the bottom of the page. One of them is going to be us describing two events that are in this table that are dependent upon each other. And one of them is going to help us describe two events in this table that are independent of each other. So let's take a look. It says, based on the data in this table, is preferring math as a favorite subject independent of a student's gender? So we have two events. Probability of math, we'll call that M, And gender. Gender could be male or female. Since we're already using M for math, let's use female. You could have used male if you wanted to. It really doesn't matter. You're going to get the same result whether you choose male or female. So, to be able to see if these two events are independent of each other, I need to find two probabilities. I need to find the probability of liking math, and I need to find the probability of liking math given the fact that you were a female or male, whichever one you wanted to do. I'm going to go with female here. So the probability of liking math. There are 18 people out of this entire survey that liked math. And out of this entire survey of 57 people, that gives us a probability of roughly 0.316. The probability of liking math given female, well, that's going to interest us in just one section of this table. So let's take a look at our highlighter here. Last time I used it, it was way too dark, so let's change it here. So let's just highlight the females. We're only talking about this yellow section. So out of those females, right, out of those females, we're only talking about a certain section. So there are only 30 females in the survey. And of those, 8 of them like math. So if we find this probability, we get 0.267. So what do we notice? By introducing just being a female, I've decreased the likelihood of liking math. So that means the gender affects whether or not you like math or not. So these events are dependent. And we can say because the probability of liking math is not the same as the probability of liking math given the fact that you were female. We can clearly see that these two numbers are different. So by introducing the fact that you're a female person, it's going to decrease the likelihood of you liking math or not. Okay, let's try a different subject. Let's try the subject of social studies. So to find the probability of liking social studies being independent of a student's gender, we can say, well, what's the probability of liking social studies? And what's the probability of liking social studies given the fact that you are male or female? Since I did female in the last one, let's do male for this one. Again, it should not affect my outcome of being independent or not. So the probability of liking social studies. So in this table, there are 19 people that like social studies out of a total of 57 people. That's 0.333. It's actually repeating, so I'll just put that up there so we know that it does not end. The probability of liking social studies given that you are male, well, that means we're only looking at the males in this table. So if I take my little highlighter here again, we'll choose a different color, and let's just highlight the males in this table. So out of the males in this table, there are going to be a portion of them that like social studies, 9 of them out of 27. So if I do 9 out of 27, I also get 0.333 repeating. I'm putting the repeating there so that I know it's not rounded. So because these two things are exactly the same, they're the same probability, by me introducing the fact that this was a male, it didn't affect the probability at all. Therefore, there was no effect. Therefore, these are independent events. So we can say these are independent events because the probability of liking social studies is equal to the probability of liking social studies given that you are male, meaning your gender did not affect the likelihood of choosing social studies as your favorite subject. Now, if you think about it, before we move on to the next page, chances are there's going to be some type of an effect, right? It's really hard to come up with probabilities that are going to be independent of each other. You could almost make a case that almost everything is going to have some effect on everything else. So when you're looking at these questions, yes, they're math problems, so we can manipulate the numbers to make it so that they are independent or are not independent. But more cases than not, it's probably going to be a case of dependent events. But let's take a look at another example here. So on the next page, it gives us some data here about the Titanic. So on April 15th, 1912, the Titanic struck an iceberg and rapidly sank. And out of her passengers, a bunch of them died. So some survived, some died. So there are some statistics here about whether or not you survived and died on the Titanic and what type of passenger you were. Were you a first class passenger, a second class passenger, or a third class passenger? Well, if you've seen the movie Titanic, you already know the answer to this question, right? You probably remember the scene where all those people that were down in the boiler room died instantaneously because nobody cared to help them, while all those first class passengers were getting on their boats and surviving. So you probably already know the answer here, but let's see if the math supports the movie and what we think is going to happen. So if we want to determine whether or not the class is independent, or the probability of being a first class survivor versus being a survivor in general is independent of each other, we have to find two probabilities. We have to find the probability that you were a survivor, and we have to find, well, what's the probability of you being a survivor given the fact that you were one of these three classes? It doesn't matter which one you choose, right? So let's just choose first class because that's going to be the most intriguing number. So the probability of surviving. So out of the total of 1,317 passengers, there were 500 of them that survived. So if I type that into my calculator, I get a decimal here of 0.380. Now, what that tells me is there's about a 38% chance if you were on the Titanic and I randomly chose you as a passenger, not considering what class you were, that you would have a 38% chance of being one of the survivors of this horrible crash. Now let's take a look at the survivors given the fact that they are a first class passenger. So if we're looking at just first class passengers, we only care about this first row. So we're saying, okay, there are 324 first class passengers. And of those first class passengers, 201 survived. So if I do 201 divided by 324, that gives me the decimal 0.620. This is a gigantic increase in probability. I went from being a 38% chance of being a survivor of the Titanic to knowing that I'm a first class passenger, now saying there was a 62% chance of surviving. We can clearly see that class affected the survival of the passenger, right? So we can say class of passenger and survival are dependent events because the probability of surviving is not the same as the probability of surviving given the fact that you are a first class passenger. Now, you didn't need to choose first class passenger. You could have chose second class passenger or third class passenger, and you would have seen that these two numbers would be different every single time. Actually, if you think about it, if you actually did all of those, the only type of class passenger that you had a smaller survival rate than the overall survival rate is the third class passenger. If you do that calculation, it comes out to be 0.255. But we did enough work to answer this question, so we'd be done. The next question says that we have these airlines, and we want to figure out if these airline times are independent upon what airport we travel to. So essentially, landing in Chicago versus landing in Los Angeles, is there a independence, or is there some type of an effect on whether or not your flight is on time or not, depending on which airport you fly to? So the unfortunate thing about this particular question is they don't do all of the work of the table for you. So they only give us the four pieces of data: when Chicago is on time or late and when Los Angeles is on time or late. It doesn't tell you the total amount of flights that go to Chicago. It doesn't tell you the total amount of flights that go to Los Angeles. It doesn't tell you the total amount of on-time flights or late flights, or even just the total number of flights at all. So we have to do some addition here. So pause the video, come back. I'm going to do the addition quickly for you, and I'll unpause my video and have it so that you can just practice adding up these columns, I guess. I know you all know how to do that, but let's just do it on our own. All right, so welcome back. Check your answers there for your addition. All I did there was add my columns and add my rows, and then saw that my columns and rows all added up to the same number of flights, 14,648 flights. So the first thing it says is to explain what it means to say that the two events, arriving on time and Chicago, are independent. So what that would mean is, to explain that, we can say arriving on time is not affected by landing in Chicago. That's like part A. They're just asking you to explain what that means. The second part is asking to show whether or not the two events are in fact independent. So if we were to show that these two events are independent, we have to prove that the probability of one event is the same as the probability of that event happening given the other event in this problem. So we can say, well, what's the probability of a flight being on time? So out of this whole chart, there are 14,648 flights. Of those 14,648 flights, 12,047 are on time. That's both Chicago and Los Angeles. It's taking both airports into consideration here. Well, if I do that, there's a 0.822 probability, or about an 82% probability of being on time. Not the greatest, in my opinion. Now, if we find the probability of being on time given landing in Chicago, well, that's a whole nother probability. Now we're only looking at the flights that land in Chicago. So since we're only looking at the flights that land in Chicago, we're looking at this section of my chart. So there are 10,686 flights that land in Chicago. And out of those flights, 8,796 of them land on time. Well, if I do that quick probability, I get 0.823. Really close, but different. So I could say these events are not independent, or they're dependent upon each other, either way. So we could say not independent. And what that means is the chance of being on time is affected by whether or not you land in the Chicago airport, right? You could say it slightly increases when landing in Chicago, so it's actually nice to land in Chicago versus Los Angeles. So Los Angeles is actually making the on-time flight probability decrease slightly. Now, these two numbers are super close, so there is a small amount of kind of independence, but they're really not, because they're not the same number, okay? All right, let's keep going. All right, so on the next page, we have a question here that is not a two-way table. Could it become a two-way table? Sure. If we wanted to make this a two-way table, we could. Okay, we don't want to because it's just a waste of our time. So let's take a look at the probabilities that they give us. They're going to give us all the information we need. So they're telling us the probability of rain, 55%, 0.55. Probability of lightning, that is 0.20. And the probability of rain and lightning is 0.15. To determine whether or not rain and lightning are independent, I need to find the probability of rain given lightning, or lightning given rain. It doesn't matter which one. I'm going to choose rain given lightning. And I want to see if that is the same as just the probability of rain. Does introducing lightning to the probability affect the probability of it raining out? So because we want to show the probability of rain given lightning, we're only talking about lightning here. So the denominator is 0.20. The numerator is the chance of rain, but we can't use the 0.55 because that is too much. That's including a lot more stuff. We want to use rain and lightning because we already know lightning's happening. So that's going to be just the probability of rain. Now, if that part confused you, just remember the probability of any event given another event is the probability of the two events happening with end divided by the probability of what was given. That's what we just did to get these two numbers. We said the probability of rain and lightning divided by just the probability of given, which is lightning. Well, if I do that quick probability calculation, I get 0.75. So we can say these are not independent. We can even say they're dependent. It means the same thing. Because the probability of rain is not the same as the probability of rain given lightning. The fact that we introduced lightning to the probability changed the probability of it raining. So that means rain and lightning have some type of a connection there. There's an association if it's raining out that lightning's also probably going to happen. Number 7, we're going to skip. It's us proving yet another way of proving independent events. I don't need to do that with you. If you're really interested in this and this is something that intrigues you, just Google other ways of proving two events are independent and a bunch of different things will pop up. I promise, right? But for right now, just knowing how to do it just this way that I'm teaching you in lesson 4 is good enough. All right, so let's skip forward here to the homework. So here's a chance for you to pause the video, come back. Try the homework first, though. Don't just jump right into it after the lesson, right? Pause the video, come back, see how we do. All right, so hopefully you paused the video, now you're back. So let's take a look at this first question. So it gives us this two-way table of males versus females and whether or not they like comedies, dramas, or reality show TV on television. Before even answering this question, you can probably guess that these are going to be dependent events. They're not going to be independent. Think about it. Now, I'm not trying to be sexist when I say this, but if you look around your friend group, I'd probably guess that more females like reality show TV versus males. They're probably more on the comedy and drama side of things. Just knowing what my wife watches on TV versus what I watch on TV. But I'm not saying that that's true for everybody, but you have to take a look at the total population. Where is the population going to sway the idea here? But let's prove it mathematically, because we always want to prove things mathematically when we can. So to do this, I need to find, well, what's the probability of being female? So in this survey, what's the probability of being female? There are 260 females in the survey out of a total of 490 people in the survey. That's going to be the probability of 0.531. Again, always 3 decimal places there on your probabilities. Now, to prove whether or not the idea of being female and liking a drama series are independent or not, I need to, well, see, is the probability of being female, given the fact that you like a drama series, the same as this? So when we're looking at this, since drama series is what's given, I'm going to highlight the drama series part of my chart. I only care about this part of my chart now. So because I only care about that part of the chart, there are 135 people that like drama series. Of those, 70 are female. Now, if you did this, you get 0.519. These are different. So we can say these are not independent. Because the probability of being female is not the same as being female and liking drama series. Now, you might be looking at this like saying, I did this differently than you, and I got the same answer at the end, that they were not independent. This second part, I'll highlight it in green, right? This second part, I could have done the probability of liking drama series given female and saw whether or not there was a change there. It would have come out to be a different number. It wouldn't be 0.519. It'd be a different number, but it would still give you this ending result of not being independent. All right, so there's a dependent there. There's some type of an association in the type of series that you like and whether or not you're male or female, according to this survey. Number two is kind of like the rain and lightning question we did at the end of the lesson. There's no two-way table here, but there is enough information to figure out whether or not these are independent or not. So to figure out whether or not these are independent or not, I need to find the probability of A given B. Well, to do that, I know I can take the probability of A and B and divide it by just the probability of what was given, and I can see that this becomes 0.6, which is the same as the probability of A. Meaning by introducing B, I did not change the overall outcome of the probability, meaning B has no effect on A. So I could say these are independent. The probability of A is not affected by event B happening. I don't even know what these events are, but I do know how to find probabilities using what I learned in lessons 3 and lessons 2. So I can find this conditional probability just using the rule. Number 3 gives us a music versus male or female survey. Like the flight question in the notes, the whole total part was not there for us, so we have to fill in some totals here. So let's just make my chart bigger to show my spots for totals. So the total of the first column is 90. As soon as I see a unfilled chart or an unfinished chart, I want to do this 100%, right? I don't want to try and pick and choose when to do this or not. Just fill in the chart. It takes a minute to just add up numbers, right? All we're doing is adding up numbers there. So I've added up some numbers here and I get my totals for all my rap and country music fans and all of that stuff. So it says, for this group of students, do the data suggest that gender and preferred music styles are independent of each other? So let's pick a gender. I'm going to pick females. Let's see if females are affected by whether or not they are techno people, rap people, or country people. Is there a connection here, right? Or is there no connection here? So what we can say is, what's the probability of liking techno? And is that the same as the probability of liking techno given the fact that you are a female person? If these two things are the same, then we know that they are independent of each other, meaning gender has no effect on your music type. So out of the techno people, there were 90 out of the total 200. And out of the females, so if I just look at the female column here, since we chose to use female as our gender here, I'm only ever really looking here now on my chart to do my conditional probabilities. So we have 106 females and 54 of them like techno. If these two numbers are the same, that means that they're independent. If they're different, that means they're not independent. So we get 0.450, and that's not going to be the same as 0.509. So just from this particular piece of information, right, we can say that techno and female are not independent of each other, right? Meaning there's some type of an association between gender and whether or not you like techno music. Well, that might not be the gender of music that you chose. You might have chose rap. And whether or not you were female. Well, the probability of rap, there are 65 rap people out of the 200 in the survey, and out of the 106 females, there are 25 that like rap music. So we could say this is 0.325, not the same as 0.236. So again, the fact that you like rap music is affected by your gender, right? So these are not independent. So each time we're getting the same answer, not independent, not independent, right? It didn't actually matter which gender of music or style of music we chose or which gender we chose either, right? So there's actually 6 different independence problems that you could have done here, right? So it's kind of hard for me to go through every single answer because I'm not going to. It takes too much time. But if you got not independent and you are confident that your probabilities are correct, I'm sure whatever you did is correct. If you really want to show me, take a pic of it and send it to me via email, and I'll take a look and see if you did it right or wrong. Okay? But here's two of the six possible answers here for this last question. So you might have some questions at this point, right? How am I going to ask something like this? Well, I might just ask you something more like this first question, where I'm specifically asking you to choose the two, right? So you might have to describe some things here to me. What's the probability of being female? What's the probability of being female given being a drama series person? Being able to show where you're getting your work from, not just saying not independent. That's not going to be good enough in a show of work type question here. You have to show the work that supports your answer. That's lesson 4. Hopefully that worked out for you. If you have questions for me, please reach out to me via email. I'll be happy to answer them, and hopefully I see you all soon.